All right, friends and neighbors, welcome back. It is time now for Chapter 5, Analyzing Ethernet LAN Switching. So we have to remember the stuff that we know about Ethernet, but we're going to pick up a new tool or a new idea, and that is how Ethernet switches work. So in this video, we're going to talk about, what is a switch and how do they work? We're also going to remember the Ethernet frame and the MAC address types that we've talked about so far. And then we'll talk about forwarding all those different types of traffic, in particular, different kinds of destination MAC addresses. And then we'll say, all right, well, what can a switch tell me about what's going on? And then what happens if I connect a whole bunch of switches together? Does that change the behavior? And then, of course, it'll be demo time. All right, time now for do you know this already? Now, some of these questions got a little bit long, so I'll explain as we're going here, and then we'll cover them all in the demo as well. All right, first up, which of the following best describes how a switch decides how to forward a frame for a known MAC address? So there's a couple things we have to know to answer this question going into this chapter. And that was that, first of all, a switch understands or has a known list of MAC addresses. The second is maybe that there's a table. It turns out that we do tables all over the place and all the time in networking. And so the table is going to have all of those MAC addresses that we already know. So when a switch understands a MAC address already, it just sends the traffic to the particular port to which that MAC address is connected. So that was A. Which of the following describes how a switch with all ports assigned to VLAN 1 forward to a MAC address of all Fs? Couple things we got to know in this one. First of all, by default, all ports in a Cisco switch are connected to VLAN 1. So we had to know that. So that describes a particular behavior, which means that all ports could reach all other ports. And the minute that we have a frame that's got a destination address of all Fs, that's a broadcast MAC address, then it goes out everywhere except for the port that it came in on. Which of the following describes what a switch does with a frame destined for an unknown MAC address? Well, we have to be able to get to all possible nodes. So what a switch does with something that it doesn't understand, in other words, it looks at a MAC address and goes, well, this is not my table, and this is not a broadcast or a multicast. Well, I got to find him. So it blasts it out every port except for the one that it came in on. We call that flooding, and so the behavior is exactly the same as a broadcast frame. Which of the following comparisons does a switch make when deciding whether a new MAC address should be added to its MAC address table? Okay, so we have to remember a couple things. One is that it's a source MAC address table. So I don't care about destination MAC addresses at this point. If I'm going to stick something in my table, I want to know that this was in the source MAC address. That is, it came from a particular node. And then the other thing is whether or not I know it already. And so that's really the big deal there. What facts are displayed by the show interfaces command? Well, this was C, and this was a little bit tricky. It was a little bit long. So the idea was that whether or not a port was up and whether or not one of the ports had a node connected to it, and then whether or not it was a fast Ethernet or a 10 base T Ethernet or a 10 megabit per second. So for this question, you had to realize we're talking about fast Ethernet in this particular kind of switch, that it had a node connected and then it was part of that group. Given the output of show MAC address table dynamic, which of the following is true? Well, that was D, and the tricky part there was whether or not there was more than one switch connected. So if you are looking at the show MAC address table dynamic, we know a couple things. We know that traffic came from a particular node down that line. But we don't know if the switch has been up forever, right? Switch table entries time out. And so it's not that this would be the list of MAC addresses that I knew from the time that I started. We don't retain all that information. And we don't necessarily know that the node is directly connected to that port. It might be several switches away. So that was the tricky part there. Okay, so let's get on to the chapter content. Assuming, even if we knew all this stuff, right, let's talk about how Ethernet switches operate. So first up, what is an Ethernet switch and where can we find them? Well, above me here is a picture of an Ethernet switch, and so a lot of times that's what they look like. But Ethernet switches or switch ports take all kinds of different styles and shapes, right? This is a wireless home gateway, right? And these ports on the back of it, these are switch ports. So everything that we're talking about today also applies to your wireless home gateway switch ports. Usually there's, 4, 5, 8 sometimes. And so that behavior is the same way. But if we're talking about a production or enterprise environment, that's probably going to be in a wiring closet or an equipment closet. And then there'll be some mounting brackets on the side of this particular switch to connect them to the rack. Now, the demos, I'm going to have IP addresses, and we're going to be pinging around between nodes. But the thing that we have to remember is that Ethernet switches work at layer 2. So they care about MAC addresses and Ethernet frames. They're not interested in IP addresses or IP packets at all, at least by default. So the basic behavior is not to care about IP packets or IP addresses. So we have to follow the MAC addresses and the frames. Now, as far as the switch logic goes, we know that we have a couple of different MAC address types. We have a couple of different Ethernet types. And so we have to make sure that we can do a couple of things. One is we have to get the frames, the Ethernet frames, to their proper destination. We have to ask ourselves whether or not there are filtering rules, right? Are we controlling traffic? Did we already learn the MAC address to the destination? So there's this question whether or not I have to update my table. And then are there other switches and can we avoid loops? So there's actually a whole bunch of stuff at layer 2 that happens. And then at the end of the Ethernet frame, you can do some error checking, right? We have the CRC or cyclical redundancy frame check sequence. So first up, we have to remember that there are 3 different kinds of MAC address. We have unicast MAC address, multicast MAC addresses, and then broadcast MAC addresses. Now, I want to make it really clear. We are talking about destination MAC addresses. So when a switch gets a frame, it looks at both MAC addresses, and it says, all right, let me look at your source MAC. Do I already know you? And if I don't, I'm going to put you in my source address table because I want to remember where you are. And then we're going to look at the destination MAC address. And I'm going to make some decisions on how to forward that particular frame based on that MAC address. Does it go everywhere? Does it go to a particular port? Do I know this destination already? And then lastly, we're also going to get to the end of the frame and we're going to calculate that CRC. And it also doesn't matter what flavor of Ethernet we're talking about. Remember that we have 2 general types of Ethernet frame. We have what we call Ethernet type 2. So if you're capturing in Wireshark, you can see at the frame here at the bottom of this slide, that says Ethernet type 2. But it also might say 802.3. These are 2 different kinds of Ethernet frame. They exist at the same time. They're both in the 2012 standard. But it doesn't matter what kind of Ethernet we're talking about. We have to be able to handle all of this stuff. So here is a really important idea. Switches learn MAC addresses. And the way that they learn is whenever a node generates traffic, right? So if I just have a whole bunch of PCs connected to a switch and they start generating traffic, which is something that nodes do the minute you plug them in real life. Not in simulators, but in real life, nodes generate all kinds of traffic. The minute nodes generate traffic, the switch goes, aha, I recognize your source MAC address and I'm going to put you in my source address table. And I'm going to tie your MAC address with the port on which I saw this traffic. Now we call it a MAC address table, but there are lots of names for it, right? It's a source address table. That makes it really clear which MAC addresses we care about. We also call it a switching table or a CAM or a constant addressable memory. So I've got an example of a switch source address table here. Remember that the source address table is all about ensuring that a MAC address can be reached. And the way that we do that is when a node generates traffic, I see the MAC address and I attach it to a particular port. So you can see if you look at the bottom of the table, the dynamic entries, these are the ones that we learned. We can see that we've got a couple of MAC addresses there, and we can see that they're attached to particular physical ports. Now, there's a couple of things that are really, really interesting about this particular snippet. If we take the first column, there's a VLAN column there. Now, all the examples in this particular chapter are going to be all the same VLAN, but there's nothing at all that says that MAC addresses and nodes can't be in different VLANs. That's chapter 8. So that complicates things. But for right now, I just want to point it out. The second thing is that there are a whole bunch of MAC addresses that the switch knows, it understands, and these are sort of coded in. And those are multicast and broadcast addresses so that the switch understands what to do with those. And then there's the ports and the MAC addresses that the switch learns. And those are the bottom entries, those are the dynamic ones. And then lastly, you can see that on the ports side, that there are a couple of MAC addresses that are connected to the same port. And that means that there was probably another switch downstream of that particular port. We'll show examples of all of that later on. Again, what do we do with traffic that is sent to destination MAC addresses that are known, unknown, broadcast, or multicast? Well, when I see a frame come in and I look at the two MAC addresses, I look at the source MAC and I say, are you in here already? And if not, I'll add it. If it's already there, then I don't worry about it. Then I look at the destination and I say, do I know this destination? In other words, did I already learn where this node was connected? And if so, I send it right to that particular port. If it's unknown, broadcast, or multicast, I'm going to send it out all ports except for the one that it came in on. That's that flooding behavior. Now, just as a reminder, these are the different layer 2 MAC address types that we have to worry about. If we look at each one of these, so I've got 3 different frames here, so I hope you can see that. And in all cases, if we look at the source MAC, right, there's one right there, there's one right there. All 3 of those source MACs are unicast, really, really important. The destinations, however, can be unicast, broadcast, or multicast. And that is what affects the behavior of the switch. And then if we add to this a MAC address that might not be known, right, then we've got all of our forwarding decisions that have to be made. Okay, to flood or to not flood, to flood or not to flood. When a MAC address is known, right, then it goes to that particular port. That's the whole point of the mapping in the source address table. In fact, most tables are mapping between 2 things. In this case, it's what port are you connected to and what's the MAC address that's there. And we'll see later on that we're going to add VLANs to this, but we'll pause on that one. If a frame destination MAC address is unknown, again, we're going to blast it out everywhere. If the frame has a broadcast destination, right, then we also flood, but this is a forwarding rule, and we saw that entry in the source address table. Now, multicast is a little more complicated. Multicast, by default, will be flooded everywhere. But we can create multicast groups, so it's only blasted out a collection of ports. Now, that's a story for another day, but there are protocols that are involved there, most notably the Internet Group Management Protocol. Now, there's probably a couple of ideas that we ought to talk about with regard to switches. First, the rules that we just talked about. Learning MAC addresses, how to forward traffic, that applies to all switches. And it doesn't matter which vendor, but there are a couple of other things that we want to get a handle on. First is, I suppose, VLANs. Now, VLANs can really mess up our forwarding or really complicate things. But fortunately, all ports start off in VLAN 1, and I will show that to you in a minute. But we're not going to talk too much about VLANs in this particular video. If you want to jump ahead and talk about VLANs, you can take a look at Chapter 8, or I'll post a link to some of the video content. But we'll cover that later on. By default, all ports on a Cisco switch wind up in VLAN 1. Now, this is also called the management VLAN or the default VLAN. I'll add another term here, the native VLAN. At least initially, the VLANs are not going to mess up our forwarding. So for right now, as long as all nodes exist in the same VLAN, all the rules that we've discussed so far apply. Now, the really cool thing about this is that because all switches are obeying the exact same rule, they all do the exact same thing. They all forward based on the rules that we have, and they all obey the same flooding behavior. And so that's the way that all of them are going to work from here on out. Okay, let's do some demos, and we'll try to cover as many of these ideas in the demos as we go. All right, so I've got a couple of topologies here. Now I'm going to eventually connect these all together. But here is a default topology, right? I've got 3 nodes connected. Now I've given them IP addresses, but I do not want to worry too much about the IP addresses here. What I care about really is the MAC addresses. And so we're gonna focus on our layer 2 addressing here. But first, let's take a look at our switch. So I'm going to go to the CLI here. And this is our initial, so I'm going to do a show MAC address table. Now there's nothing in this MAC address table. Now if this was real life, the minute I connected these nodes to these ports, right, they would have generated lots of traffic. Operating systems are very chatty. But in this case, they have not, because the simulation doesn't cause them to generate lots of traffic initially. So until I generate traffic, there's nothing in the switch source address table. So it hasn't learned anything yet. Now let me show you something else. I'm going to do a show VLAN here. There's VLAN 1 right there. And we can see that by default, all of my ports are in VLAN 1. That's really, really important because the VLANs are not going to create boundaries for us here. Now this is our default condition, right? This is also called the native or the management VLAN. All right, so that's what we know. Let's also do a show interface. Now, if I do a question mark here, we can see that we've got a lot of sort of arguments that we could use. If we do a status, and I think that's the one from the chapter. If we take a look right up here, we can see that I've got 3 nodes connected. The rest of the ports are showing not connected. Now I can also see that these have an F in front of them, the interface name. So that makes them fast Ethernet. So that's 10100, right? And so they're not gig, they're not just 10 megabit port. I can also see the VLAN to which these ports are connected. So these are all handy ways to get a little bit more information about a particular port or how your switch is configured. The first thing that I want to talk about is how we forward traffic. So I'm going to open up the simulation here. And what we're going to watch for, and we have to sort of be aware of this, right? When I'm going to ping between these 2 nodes. So I'm going to send a ping in this direction right here. And when I do that, if I look at the ARP table, right, there are no entries shown. So in order to build an Ethernet frame on PC1 here, I need to learn the MAC address of the destination. Now I can't remember, we haven't talked too much about ARP yet, but the address resolution protocol has one job, and that is to learn the MAC address of an IP address destination. So the first thing that I have to do is process my host routing table. I would find out that they're on the same network, and then I would send an ARP request after looking in my ARP table and finding no entry. And again, the point is to find the MAC address of the destination. Now, this video is not about ARP requests. I will put a link to that. I know that we're going to talk about it later on, but that's what's going to happen. For us today, the important thing about ARP is that it's a broadcast frame. And so we're going to watch what the switch does with a broadcast frame. That is to say, a frame with a unicast source MAC and a broadcast destination. Okay, so I guess I shouldn't have closed that. So I'm going to ping 10.0.0.2. Now there's also going to be a whole bunch of other stuff that happens, right? The switch is suddenly going to learn where PC1 is. It's going to flood this broadcast frame out. PC2 will respond, and then it's going to learn where PC2 is. So what we'll try to do is look at the switch source address table as we go. All right, so I have sent that out, and we can see that we've got an ARP message here queued up and an ICMP. The ping sends ICMP echo requests, and the ARP message is going to go out. Okay, so the ARP message goes out. There it goes, and it gets to switch 0. And now it goes, look at it. It went everywhere. It goes to all of the ports that are connected, except for the one that was the source. Now let's take a look at the switch source address table. Let's see if this updates as fast as we want it to. Look at that right there. We immediately learned that this MAC address ending in 04D6 was connected to F0/1. So the switch learned where PC1 was. Okay, let's keep it going. So now the ARP reply comes back. Oh, let's look at a couple other things here. So when the switch, the MAC address goes out, or the ARP request goes out, we can see, hopefully you can see this in the video, right? This is an all F's destination. That's a broadcast MAC address. And the point is to learn the MAC address, right, of the destination. So this message goes out and says, hey, everybody, who's got the MAC address that goes with this? Now, PC2 responds with an ARP reply. But this is unicast. This is the destination, right? It's going right back to PC1, right? But now the switch knows where PC1 is because it learned it. And so this message, if it was unknown, if the switch didn't know the MAC address, would go down here to PC3, but it will not. So we keep going. It just goes over to PC1. Now the switch at this point now knows where they both are. Now it doesn't know where PC3 is yet. So another little nugget of information is that PC2 and PC1 are going to have a conversation now. And PC3 is not going to know that it's going on. It's not going to be part of it. It's not going to be able to see the traffic. And that's another beautiful thing about switches, is they filter traffic only to the correct destinations. So even if you were a bad guy listening in, you would only have seen the ARP request messages. So if we follow this through, we'll just see that PC1 and 2 are having a conversation, and PC3 is on the outskis. So that's a really important detail. Now there's a message that just popped up here that says STP. Now I'm going to let this one go. This is a multicast frame. Not that we care about this for a switch forwarding rule. This actually came from the switch itself. So a couple important things here. One is that switches actually have their own MAC address. Two is that switches engage in protocol, so they generate their own traffic. This particular message is how switches protect us from loops, and this is the spanning tree protocol. So I'll just we'll let this go, and then we can see the conversation continues until it's done. The default is on Windows is four times. Just as a reminder, we've learned where these MAC addresses are, and they're the dynamic entries. Now, if I do a show MAC address table, what's missing from this is the static entries that I would see on a regular switch. So I could say, well, what are the static entries? I don't have any. This is a simulation, so it's a little weird. The other thing that's important to remember is that the source address table has an aging time. Each entry in a table has a time associated with it. The time is typically 5 minutes or 300 seconds. So after 300 seconds, the switch forgets these MAC addresses and will relearn them. Now that's nice because old entries or stale entries are not retained in the source address table or the CAM table. Okay, so let's do a couple more examples here. Now I'm going to connect the switches. Oops, let's use a crossover cable. And I'm going to connect the switches together on port 24 on both of them. What this will do is figure out that we've got a couple of switches connected to each other, but what we haven't done is transmitted any traffic between the switches. So what I'm going to do is we're going to ping between PC1 and 3 now, and we're going to see that ARP request go across, and then we'll examine what actually happens, and then we'll try to communicate with PC4. So we'll run our simulation again, and instead of pinging PC2, what I'm going to do is ping PC3. Now remember, this is going to generate ARP request. Oh, let's take a look at that too while we're here. So if I do an ARP-A now, you can see that PC knows the MAC address for 10.0.0.2. So again, here we have another table that's a mapping between, in this case, IP address and MAC address. The switch source address table is a mapping between MAC address and port numbers. So let's ping 3. We're going to get our ARP request, and this is going to be blasted out everywhere. But the fun part in this one is how far does it get blasted out? So here we go. We can see the ARP and the ICMP are queued up. There goes the ARP. So as a reminder, right, we have a broadcast MAC address here, and we know what the switch does with the broadcast MAC address. It goes everywhere on switch 0, but it went across to switch 1. What does switch 1 do with it? It blasted out all ports there. Now in this case, we just have one port, right, to make the simulation or the demo go quickly. But this goes everywhere. Now who responded? Just PC3. Okay, so PC3 responded with an ARP reply. And again, the switch knew where PC1 was because it learned where the MAC addresses are. Okay, so they're having a conversation now. What if we take a look at the MAC address table for switch 0? Oh, and let's do this too. So we know, let's remember our host name command. So when I'm looking at the different switches, we'll call this switch 0, and we'll do a show MAC address table. And now I have 3 in there. But this is very strange. What's going on? The entry for PC2 aged out. Now I could put that back in here. But what's happening? Well, first of all, I learned where the MAC address for PC3 was, right? Ending in 9C7C. But I also have this one. What is this on port 24? Well, on port 24, I have traffic that was from the other switch. And so this is that STP traffic coming across. So if I ping all the way around, right, to everybody, well, before I do that, let's look at switch 1, and we'll do our hostname command here as well. We'll call this switch 1. And I'm going to do a show MAC address table here. I can see that I picked up this MAC address here. It's 04D6. That's PC1. But switch 1 here believes that PC1 is connected to port 24, but it's actually connected to port 1. Why is that? Well, from the perspective of switch 1, everybody on my switch looks like they come from port 24 because that's where the connection actually is. And so that's why in the source address table, we see that it's connected to PC or to port 24. Okay, so we'll let this continue. We'll go through this. And that's why the switches learn from each other right there. That's why they picked up the MAC addresses. Now, as soon as switch 1 and switch 0 generate traffic, everybody will be in the same, or everybody will appear in the source address tables for the various switches. Let's now, what I'm going to do is ping around. Let's do it from the perspective of PC4, I think. And then we'll learn where everybody is. So on PC4 now, I'm going to ping all of the nodes. Now we're not going to watch this happen. In this particular case, it'll take too long. But I'm just going to ping everybody. And then we'll analyze what we see in the tables. So I'm going to ping 01. We'll ping 02. And we'll ping 03. Now again, ARP is not really part of this particular video or this particular chapter, but it's part of what we do. So now we can see that our last PC, PC4, has learned the MAC addresses of all these IP addresses, which allows us to communicate. Let's take a look at the switch source address table on switch 1. Look at all of these addresses. Now I've got 4 nodes, but why are there 5 entries? Well, one is the other switch. So we can see the MAC addresses for all the PCs, right? 85E0, right there. We've got PC1, PC2. But we also see PC4 in here, and the MAC address for switch 0 is in there as well. That's this one. This one right here is going to be, whoops. This one right here is going to be our other switch. So that's why there's more entries than the number of nodes. And we can see that all of them appear to be connected to port 24. But again, that's the perspective of switch 1. If we take a look at switch 0, its MAC address table, we can see a little more variation, but we see that there are 2 down port 24 from this switch's perspective. Remember, this is port 24 and this is port 24 as well. And then all of the other ones. All right, let's do one more thing here. And this is how switches protect us. So I'm going to add another switch here. I don't have to add any other nodes, but I'm going to add another switch and we're going to connect them in a loop. So I'm going to connect these here. To each other. Now, in Ethernet, loops are bad because broadcast traffic would continuously circulate. And there's no way at layer 2 to remove broadcast frames. So what we do instead is we have that protocol running, spanning tree. And so if we watch our simulation here just a little bit, the switches are communicating these, well, they look pink to me, but we've got all of these messages. Maybe we'll get rid of DTP for right now. We don't care about CDP and DTP for this video. So look at all of this STP traffic that's floating around the topology. This is the spanning tree protocol, and the spanning tree protocol, thank you Radia Perlman, is the thing that switches use, the protocol that switches use to prevent loops. And so what ends up happening is that we can see that this one is amber or orange. And if we take a look at what's going on, let's see if this simulator can show spanning tree. Okay. Now I'm gonna point these out. This is not what this video is about, but we've got some switch has been elected as the root. That's what all of this is. And then we have my bridge's ID. In this particular case, it'll be switch 0. And if we take a look right here, port 24 has been blocked. That's why it's amber. So spanning tree automatically blocked it. Now from where the block is, I know that this one is the root. Okay. This bridge is the root. It's the root of the spanning tree. And it is the basis of the topology now that the spanning tree protocol used to break all this up. Now, that's not what this is about, but that's what actually ends up happening. And so that is also going on the switches to save us from connecting topologies like this. But there we go. So that's how switches record where nodes are in source address tables. It's how they do their forwarding. It's how they keep track of where nodes on other switches might be. Remember that it's all the perspective of a particular switch. It's not where nodes might actually be connected. So there's a lot of processing that the switches go through to forward traffic. Remember that they're examining both the source and the destination MAC addresses. The source addresses, whether or not they should be added to the table, and the destination MAC addresses for the actual forwarding. Switches also do error checking. They also do some level of protection for us for loops with the spanning tree protocol. So a lot going on at layer 2. All right, the look ahead for this week, right? So next chapter builds on this one. It is configuration of basic switch management. So we'll look at, how we would do some IP addressing and some subnetting for management, specific to management, and then some of the connections. Now we mentioned that you can connect to a switch or a router via protocols like SSH, HTTP, and so on. But we'll talk a little bit more about them. We'll talk about some of the services that we might need in a fully functional topology. and then some of those security fundamentals. So it's really, really important. This chapter isn't an enormous chapter, but it has some really key ideas that we really want to latch onto as far as how traffic is handled and those tables. Then we can look and see what's going on. So really important to remember what's going on in chapter 5. So this has been analyzing switch operation. You know, switches, how they work, the Ethernet flavors and the MAC address types. We looked at forwarding traffic, right? All of those different kinds of MAC address, what happens, how it works. We threw in address resolution protocol just because it's there. We looked at some ways to get information from a switch. And then, of course, what happens when you connect multiple switches together in a loop or without a loop. And then we did some demos. All right, like and subscribe if you are owning Layer 2, or if you're preparing to own Layer 2, that's okay too. No matter how you've got your switches connected together, may those packets or frames always reach their destinations. And remember, this is certification. You can do this. I'm going to do it with you.